Okay. Do you like it better down here? Yeah. Yeah, like you said, like, are you like, I know. Besides, like, the here and there, so it's like, yeah, so I was trying to get for like it grows. Yeah. Oh my god, that's. I'm not
like squeezing the last struggle.
I see.
Okay, so today's class, part of today's class is about kinematics of a differential drive car, and one of your labs, Lego labs, would involve you making a car and controlling it to do line following and things like that. So this is a really intuitive car or easy to build car. Your conventional car is not a differential drive car. So this car, differential drive car, has two rear wheels, and those rear wheels are powered. The left wheel has a motor, the right wheel has a motor. In the front there's a caster. Okay, a caster wheel. There are no chairs here. Usually that chair is caster wheel. Okay. So if you look at that chair there, the wheels on that chair, that is caster wheel. So the property about caster wheels is that if you push it straight, it goes straight. If you push the left, it will go straight. The wheels will orient towards the direction which you're moving, pushing it, and it will go that way. Unlike these wheels, the rear wheels, they can only move forward, right? They cannot move to the side. The way your car is designed is either you'll have the front wheels powered or the rear wheels powered, but they'll have a single what do you call it? Single motor. You can say it's not a motor, but think of it as a motor spinning either the front or rear wheels. Sometimes you have front as well as rear wheels powered, but the turning is done by virtue of steering the front wheels, right? In this case, turning is done by spinning one wheel, say the right wheel, faster to the left wheel, so it'll turn this way. If you spin the left wheel faster and turn that way or clockwise. Okay, so that's the difference. Steering is in general harder to implement on using Lego, so we'll stick to this car. So what I'm going to do today is describe how you can model the car, describe its motion, and we'll end up doing a simulation and also doing an animation of a car. Okay. So this is where we'll use some of the stuff we've developed so far. We've looked at rotation matrices, and they're going to be an integral part of the kinematics here. Okay, so let's get started. I'm going to first start off with the baseline frame or the reference frame about which I'm going to describe motion. So let's assume that the car is like so. So it starts off this way, and then it moves because the left and right wheels move, and ends up in a different position. Okay, clearly let's assume that it actually turns when it moves, so I'm going to rotate the car. Rotate, I think left would do it. Okay. Okay, so the car has turned, and I need to get rid of this. So when it turns, my frame changes. So those two coordinate frames would, let's call them x1, y1, and let's assume that the car has turned by angle theta with respect to my original axis, or x0. Okay, so in this case, x0, y0 is the global frame or the world frame, okay, which is going to be fixed. It's not moving. We're going to try to describe the motion of the car with respect to that frame. So imagine that frame is the corner of this room, the car is moving, you always want to describe the motion of the car with respect to that frame, right? So then you can do things like get it to go to a corner, or navigate through obstacles, provided you know the location of the obstacle with respect to that frame. And x1, y1 is the local frame that moves with the car. So it's fixed to the car the way it is shown there, and it actually moves when the car moves. Okay, so that is fixed, that is moved. What we do is we try to keep a track of a very special point, this point, xy. Okay, this point is exactly midway between the two wheels. And let's assume that we know the width of the car. So the width is 2w, but let's say that w is the distance from the midpoint to one of the wheels. It's the same distance from the midpoint to the right side, same as left side. Okay, so with that we can now start talking about how to do the kinematics. So we're trying to keep a track of point P. We will keep track point P, which is given by x, y, right? And we'll also keep track and theta. Okay, theta is the angle made by the car with respect to x0. So once we know x, y, and theta, we pretty much know where the car is and how it's oriented. Right? We want to know the location and we want to know the orientation. And this is a two-dimensional problem. We're only interested in x, y. There's no z involved because the car can only be on the ground on which we put it. Okay, so let's talk about how do we find x, y, and theta. That's our goal. Okay, so it turns out you cannot directly find x, y, and theta. Typically, you know the velocities of the wheels, the left and right, and to find x, y, and theta, you have to first find relation for velocities and then either integrate numerically or analytically to find x, y, and theta. So what we know, I'm going to write what is given. Let's call the velocities of the left and right wheel as phi dot L and phi dot R, which is the angular velocity of the left and right wheel. Right, that's all you can control. You can only control the speeds, and that speed determines how you're going to move. Okay, so let's see how to get from velocities, phis, to x comma y. Okay, I have to redraw that figure. It's easier to explain it with that, so let's redraw this. Okay, so what I'm going to do is I'm going to try to find the velocity of point P in frame O1, X1, Y1. Okay, so the velocity of P would have two components. Would have P. Our notation is P1 is the position of P in frame 1. If it was P0, it would be position frame 0. And we're taking track of the velocity because we know the velocity is the left and right wheel. So there are two parts to the velocity. There is an x velocity and there's a y velocity. So let's write the x velocity. Okay, so let's think what happens if we spin the right wheel. Okay, the right wheel spins with angular speed of v dot r. Okay, and the left wheel is stationary. So if phi dot r is not equal to 0 and phi dot l equals 0, so what will happen is the point P would pretty much pivot about the left wheel, right? So this is the initial position. Because this is at rest and only this one, the right one, is turning, it'll end up here, something like this. So the point P has moved from here to here. So the question is, what is this distance? So it's going to be, first of all, okay, so first of all, what is this distance? If you know that distance, then the other one is just, it's an easy calculation. So this distance, so we'll assume that the radius of the wheel is r, small r, and so if phi dot is the speed, then r times phi is the angle turned by the wheel, right? For a circle, if this is r and it turns by phi, then this is the arc length. This phi. So the speed is going to be r times phi dot, right? And so the distance, the velocity is going to be r times phi dot r. Okay, but this point is midway, so this distance is r phi dot r divided by 2. So the motion of P, because the right wheel moves, is r phi dot r divided by 2. That's only if the right wheel moves, left wheel is stationary. We can use the same argument for the left wheel. Move the left wheel, keep the right wheel stationary. You'll have the motion of the left wheel as r phi dot l divided by 2. So the net motion of or the net velocity of point P in the x direction is 0.5 or half r times phi dot l plus r times phi dot. Okay, is that clear? So that's the x velocity. The y velocity is, well, it's the velocity in this direction. So the x was in that direction, straight direction, x1 direction, and y is the velocity in y direction. You turn the right wheel, turn the left wheel. What's the velocity in the y direction? So it's not going to move in the y direction because that's the property of a wheel. You can only have a forward speed. You cannot have a tangential speed. So that's velocity in the y direction. And finally, we need to find a formula for theta dot. Theta dot is the rate of change of the angle made by the car as it is turning. And so we have to use some sort of trick like the previous P1x, P dot 1x for this one. Okay, so same thing. If the left wheel is stationary and the right wheel turns, okay, let's do a drawing here. This is P. So assume that this is at rest. The right wheel turns. Okay, so this distance is 2w because w is the distance between P and one of the wheels. So the angle, the speed in the theta direction is going to be r phi dot r. So the angular speed in this direction, which is theta dot, is so this is the reverse argument. You know the arc length. You know the radius, okay? So 2w times theta dot is going to give me the arc length, just like r p dot was obtained. The same reasoning as this. If r is the radius, p is the angle turn, then the speed in this direction, or the arc length direction, is r times p dot. Similarly, we have 2w times theta dot equals r times phi dot r. Okay, so with that we can write. I'm going to write a formula for theta dot. So I need to move okay. So but that's the angle turn, and you can see that the angle turn is counterclockwise. So the speed is, a convention is, if you go counterclockwise positive, so it's positive because the speed is counterclockwise. You can use the same argument for the right wheel stationary and left wheel turning. So if this is stationary and like this and turns, then you'll have a similar formula, but now you'll have a clockwise rotation. This is only for right. So we can write both wheels turning. Then we would have theta dot equals r times phi dot r divided by 2w. That is counterclockwise, so positive. And if the other wheel turns, you know that it is going to be a clockwise, so we put a negative sign. Okay, so that is the angular velocity in the z direction, right? Z direction points out of the plane. Okay, so I'm going to summarize all of this in a single, yeah.
Since the wheels are rotating, should there be a velocity in the y direction as well?
Instantaneously, no.
Okay.
So when the
Very
when the so this is the instantaneous motion. So this is, the lines are exaggerated. This is exaggerated. It really means very small. But yeah, if you have a wheel, it will not move to the left. That's the. By the way, this is also a model of a unicycle. Same model. Bicycle, same model. The rear wheel cannot turn in the left. It can only go straight. The actual motion, as you see, will involve moving in the x and y. So that's I'm coming to that. Okay, so with that, let me summarize what we have so far. So I wrote down a formula for P1 dot. It has three components: P dot 1 in the x, P dot 1 y in the y, and theta dot. And those were these things: r divided by 2 phi dot r plus phi dot l 0, and r divided by 2w times phi dot r minus phi dot l. Okay, the key thing is this is motion in frame 1. Okay, the frame which is attached to the body and rotates with it. Eventually, we want to relate everything in frame 0 because the world frame, we want to keep a track of everything with respect to the frame which is fixed. So how do we get that? So let's get to world frame P dot 0. Okay, and this is where you'd use the rotation matrix. We've seen that if you have the vector in frame 1 and you want to find the corresponding vector in frame 0, then they two are related by rotation matrix. So the formula is, and this is taken from concepts from the last class. See notes. But the rotation matrix is simply cosine theta minus sine theta, cosine theta, and then zeros and ones like so. Okay, so that's a simple multiplication of two matrices with a matrix and a vector. If you do the math on that, you get P dot 0 equals, I would write x dot y dot theta dot, because what is P? It's basically the position of point P, which is x comma y, and of course theta is because I also want to keep a track of rotation. If you multiply those together, you get something like this. So you can see that the velocity in the world frame involves an x speed, a y speed, and rotation about the z-axis. Unlike P, which had a 0, Py which had a 0. So we found the rate of change of the velocity of the point and theta dot. Eventually, if you want to keep a track of the position, then you got to integrate that equation. Right? You want to find x, y, theta. How would you do that? How you have to integrate. This is a function of time, so you get dt there and integrate each of those equations. That's the input. The only thing you can control in this robot is the speeds of the left and right wheel. Okay. So you specify these two numbers. They could be functions of time. you could integrate the third equation because this is known. You could integrate theta dot to get a theta, then sub in the value here, theta, and then integrate that other equation to solve for x and y. That's one way to do it. You can find a formula, but not always you can find a formula. So what we do is, the way to do this without worrying about special integration forms, anything, is to use a numerical method of integrating. So numerically, we'll actually do numerical integration of that always, and we'll use MATLAB to do the integration. So the idea is which comes from, if you've done, all of you have done some kind of a numerical methods course, right? If you have a differential equation, ordinary differential equation, like so, in order to find the x, y, and theta, you need to specify the initial condition. So where this car starts from, what position. It could start from 0, 0, 0, and then you integrate using Euler's method. That's the most easiest one, the simplest one, but it's error prone. And then you have Runge-Kutta, and then MATLAB has some fancier ways of doing it. So I'm going to show you, just sort of refresh you on how to do this using Euler's method. Okay, it's a very simple way of doing it, and then we'll actually use some of the functions which MATLAB uses, so we don't have to actually write the integration. So let me write that down. We will use, so given phi dot r as a function of time, phi dot l as a function of time, and initial conditions, which is x of 0, y of 0, theta of 0, we can use numerical integration on 1 to solve for x as a function of time, y as a function of time, and theta as a function of time. Okay, so that's what I'm going to precisely do now, and then show you MATLAB code which can do that. Any questions on this so far? Questions? Okay, so here is how you do it. So the first equation is x dot equals r divided by 2 phi dot r plus phi dot l cosine theta. X dot is can also be written as dx dt. We can also be written as x ti plus 1 minus x of ti divided by dt. And I'm assuming that these points are very close to each other, you can do this. The definition of dx dt is t goes to 0, right? When you do numerical integration, you will have to introduce a finite non-zero t, and that's where the error comes, because calculus wants it to be very, very small. So you can expand this out and write x ti plus 1. This is telling you the position at a new time I plus 1 given x of ti plus dt times everything on the right hand, on the left hand side, r by 2 phi dot r plus phi dot l cosine theta. Okay, so what I did was I moved things around to solve for x ti plus 1. So from this to this. So you can also write a formula for y, write the expression for y, write dy dt, and then simplify it to get this. And then finally theta at I plus 1 is theta ti plus dt r divided by 2w phi dot r minus phi dot l. That's it. Okay, so what we do is, with this formula in MATLAB, we define dt, something which we choose, phi dot r, phi dot l. Okay, we assume that x0 is equal to y0 equals theta 0 equals, let's say, 0. But you can start with any other point, doesn't have to be 0. Let's call this 2. And use 2 to find, let's say, x dt, x2 dt, and so on. Similarly, you can get y dt, y2 dt, and so on. And same for theta, theta dt. So you keep doing that that's a algebraic formula, right? Everything on the right hand side is known. You keep doing it, put it in a for loop, and just keep doing it till you get from the initial time all the way to your final time, whatever you choose. So I'm going to show you some MATLAB code which does that and do some animation. Files first and see what it does. Change folder. So I drew the car as a triangle, but you can draw it as a rectangle, whatever you want. So it just went straight. Let me show you what's going on in the background. So these are very standard things. Close or clear all. We move on to the point where we want to the actual simulation. So I'm going to start with 0 seconds. I want to go for 20 seconds. The delay is just for the animation. I can do it fast or slow by changing the delay. I make time from 0 all the way to end. I want 100 times t end. That's just something which you don't have to worry. You can just put 100, not a problem. Phi and r. This is basically the speed of the left wheel, right wheel. I initially put all zeros, and then what I do is I actually want to put some numbers to the left and right wheel. I divide the 20 seconds into first 5 seconds. I want the left speed to be 10, right speed to be 10. From 5 onwards to 15, I want it to be the same speed. Well, in this case, I have the same speed set for both wheels. That's why no wonder it was going straight. If you change this to, so now I've changed the left hand. So this is my car. Left hand is up, right wheel is down. If I change the speed of the left wheel, make it go faster, then I'll see the car turning clockwise. Right? So let me run the code and see if that's what happens. So it goes for 5 seconds straight, and then it starts turning to the right, and then it keeps going straight because from up to 15 seconds it's supposed to turn right, and then it's supposed to go straight. These are numbers defining my car. The radius of the wheels, width, which are defined. L is something which is only used for animations. Basically gives the height of the triangle, and this is where the bulk of the say heart of my code is. I tell the code what my speed is at that instant of time. So there's a for loop which runs from 0 all the way to time t. I pick a speed. I go to this function which I wrote, Euler integration. Okay, it does exactly what I wrote down on paper. So I actually I didn't quite write it that way. I split it into multiple steps, but essentially it is this piece. So given the speed 1, this is time ti, it finds the x at ti plus 1. Given the velocity times the step, which is dt, and it just keeps track of that. And I just put it in a way that it is easy to read. I could have potentially put everything over here. And then the animation piece is just drawing a triangle. You do not actually need to specify. These are actually the vertices of a triangle. You can see that the last one, I don't need this. This actually should not. This just makes it complicated. Let me get rid of this. Okay, now it's better. So there are 3 vertices for a triangle, and those are the vertices. Right? So one vertex is at the. So it's basically, if you. I know some people came There's no way I can. Okay, I can draw it maybe here. This is what it is. Okay, the coordinates of the left point, since this is W, is going to be minus W comma 0, right? The right one is W comma 0, and the length is L, so this is going to be X is 0, Y is L. X, Y. So all the X vertices for the triangle are X vertices are what? Minus W, W and 0, and then the Y vertices are 0, this one, 0 and L. So I need to, the MATLAB requires me to supply the X and Y vertices this way, and so that's what the code will have. It will have minus W, W 0, 0, 0 L. I hope that's how it is. Let's see. Okay, I switched the order a little bit. Maybe, well, let's see if this works. I now doubtful this will work. It'll do the plotting. Oh, it does. Okay, it does. Okay. Anyway, so that's what I think. The order actually matters. If you don't give it for a triangle, it's not a problem because it's only there's only one way. Well, you could either specify clockwise or counterclockwise, and it will actually plot. If you take a square and you specify this edge, then this edge, then this edge, and this edge, it will not show a patch with for the whole triangle. For the whole rectangle, it will actually show you 2 lines. So you have to actually specify these corners in either counterclockwise direction, this, or clockwise. Do not specify corners. This corner, it will actually it will not have a patch on the whole rectangle. The order matters. You can try doing it yourself and figuring it out why it doesn't happen, because it takes those vertices and basically puts a patch or paints that whole figure depending on the direction you specify. Okay, so that's using Euler integration. Now it's just a pain to write your own integration, and there should have been a better way. Turns out that MATLAB has other ways to do it, and I wrote this code in a different way. I use a function called ODE4. So when MATLAB came in 2006-07, they actually had ODE4, which was a part of their library, and they used to supply it with MATLAB. And since then, they thought ODE4 was so simple, it was not very accurate. In fact, it is accurate only if the step size is very small. So they stopped giving ODE4 with their package. So you will not have this in your MATLAB, but you can download it from MATLAB. I put this here because some of you, maybe 2 years back, took numerical methods, learned of ODE4, and this is not my function. This is made by MATLAB. So you see, it's very it's written in a certain way, which follows their documentation. But I thought I should write the same code using ODE4. So here, the difference between that code and this code is that instead of having Euler integration, which is a function, I used ODE4, which is a MATLAB inbuilt, but it was inbuilt, and called differential drive, which is my equation. So that way I do not have to write that H and so on. There's a specific way in which differential drive takes equations. It's actually, if you go to differential drive, you should see this function. So here also I did a different, I had a different way of writing the code. Remember, for the earlier what I did was, so you see that there was a function animation, there was a function differential drive main, that was my main file which calls the files, and then integration. Here what I did was, my animation is a part of this differential drive main. So you can actually have multiple functions within one function. So here we have function diff drive ODE4 main. Then if you scroll down, there's another function, differential drive. That's actually the equation which I wrote down on paper. That this is the formula that I derived in class today for P. It's actually P.0. I also have the function rotation here. Not necessary, but I put it down there. the function animation is also here. So you could actually write lots of functions within one function, and this is something which I had not told you earlier. Sometimes it's nice because that way all your code sits in one place. The disadvantage, however, is these, when you write these functions, they can only be accessed by this file. So if you want to call a function from another file, then it will not know that animation sits in over here. So that's why you want to put it in different places. So let's see what this code does. The only difference between that and this code, I think, is I think it's the same thing. I'm pretty much sure it's the same thing. Just turns to the left or upwards, and that's because what I did was I just made the right wheel to turn instead of the left wheel. Okay, so your homework will be based on modifying this code, and I'll post this code. Okay, so what the code does is it draws, well, abbreviates a car. Now, if I gave you a car and made you drive a car, you could potentially do this very easily. Let's say you're physically driving a car. To get this to work, it was not very easy because you can only control the left and right wheel, and it's not very intuitive to control them. So the way I did it was by trial and error. The code which does that, remember I was doing phi L and phi R, and I was changed 1 to 11. Here I had to do a lot of turn clockwise, straight, turn, and this was done by trial and error. So I want you to go through the, I guess, this is going to be very much trial and error when you do it for homework. The way I did it was I essentially started off with nothing like this. Control R, no, yeah. So this is what I did. I saw it doing, that's a semicircle, it looks like a C. Okay, then I went and said, okay, let's try to draw the A. So then I uncomment this. So I did, goes there and then goes straight. Okay, that's beginning to do the A. Then we'll uncomment this part. See what happens. It goes C and then down, and then it actually turned a little bit. This is to initiate the A. Okay, so that's okay. So this is how I did it, and I just want you to appreciate that it is not easy to do these things with a car, especially if you have only access to the velocities. What you're doing is trying to figure out X and Y, but you can only control the phis, and that is so hard. It's easy to drive a car and do this, but will be very hard if you try to only. So yes, that's how I did it. And so the homework is you trying to draw your initials using this code. Eventually, I will show you can actually use optimization to do it. So you tell the optimization you want it to go on this trajectory, and it'll actually do it for you. You don't have to go through this trouble of doing it by trial and error. Okay, so that is your homework. It shouldn't be too much of work, I believe, but it is not. You got to do trial and error, right? Okay, so we'll actually take the mobile cart later on, and besides the lab, I'll also have more things. A pin joint. What is I would say the most famous joint? Your door would have a pin joint, right? It makes motion along that axis. Then there is a prismatic joint. A prismatic joint has the property that it will only slide X motion. Okay, not too many prismatic joints. Anybody give an example? I think your elevator would have a prismatic joint, back and forth motion. Universal joint allows motion along two axes. Okay, now you could think we could make this by using two pin joints, right? It's actually two pin. When you have two pin joints, and such that the axes pass through each other, you get a universal joint. But you could make the same joint using two pin joint, except that you'll have to have like an offset. This is used only when you need to have the system to be more compact. A gimbal joint is rotation about 3 axes. Okay, it's used some places but not very known. And the cylindrical joint has 2 degrees again. It has rotation and translations, can rotate and translate. So these are specialized joints which normally are not used unless there is a specific constraint, like, typically if you want to pack everything compactly, then you want to use this joint. The 2 things we're interested is rotation and translation, right? And we'll only look at, how do I kill this? Prismatic joints, and we'll denote it by D. This one does linear motion, and then revolute joint. We'll denote that by theta. It's the rotational motion. Okay, so here is a general illustration of a manipulator. I'm only showing revolute joints, but you could potentially have prismatic joints. So this keeps going, and somewhere you would have the last joint. Okay, so some terminology before we start doing kinematics. We'll start naming the links from 0. So links will be 0, 1, 2, so on. So the 0th link is the ground link. It doesn't move, but that's a link. Link, this is link 1, 2, so on till nth link. Okay, 2 links are connected to each other through joints, and the joints will start naming them from 1. So this is joint 1, joint 2, this will be joint n. So joint n is connected to link n-1 and link n. That's the key. Okay, so I'll write that down. Joint, let me write joint I is connected to links I-1 and I. So this is where frames, which we talked about earlier, will be very useful. What we'll do is essentially attach frames to each of the joints. Okay, so I'm going to draw another link here. Help me later. So okay, so I'm going to draw a random link like this. Let's call this xi, yi, zi. Okay, and let's have another one here. Let's call this xj, yj, cj. So the key is that I occurs before j. So it's a serial chain, and this is the ground frame. J is further away than I is to the base link. the key here is to link one frame to another frame, and by keeping track of frames, we are actually keeping track of positions of one point with respect to another. So I'm going to define I minus 1 or Qi, which is the transformation. Okay, well, we'll call it the homogeneous transformation. We denoted homogeneous transformation with H, but I'm going to use A for the homogeneous transformation, linking I to I minus 1. Okay, the Qi is nothing but, it's the degree of freedom. Degrees, so this is something which you got to be comfortable. Degrees of freedom. Degrees of freedom is telling whether it's going to be di, which is prismatic, or theta I, which is revolute. So each joint would have a frame, like I've shown xi, yi, ji. That joint could have either linear motion, it would be di, or revolute motion, which will be theta I. So that's why I wrote Q. When we are trying to relate one frame to another frame, I'll use the notation T. And this is a map from, this basically maps one frame to another. So let's call T, J, I. So remember, J was further ahead than I in the illustration. If I want to find that, then it will be, so remember when you did rotation matrix 0 with respect to frame 2, it was rotation matrix of 1 with respect to frame 0, rotation matrix of 2 with respect to frame 1. You multiply them, you get the net rotation matrix. Similarly for homogeneous transformation, so you can write I plus 1 I, A I plus 2 I plus 1. You can combine all these, and that's only true if I is less than J. Okay, that is, J is further away and I is I is closer to the base link than J is. If, however, you had I equals J, then it would simply be I. And then if I is greater than J is not allowed, because our definition is J should be closer than I. Sorry, I should be closer than J to the base link. Okay, so here is some as an identity which is sometimes useful if you want to find, to TJI is known, J with respect to frame I. If you wanted to find the opposite, okay, this is basically saying you can relate this frame with that frame, that's J with respect to I. Or what if you wanted to find this point with respect to that frame? So you need to find the reverse. That actually comes from the for the inverse. So you take this first formula and then take the inverse of it, right? So that will go here, and then you take the inverse and you get the other. So that is just, we're just getting started. I'll stop here, but